please welcome Dr. Leclerc for his seminar, New Polymerization Methods for Plastic Electronics.
Thank you very much. Thank you. So thank you very much for the invitation. What I like in the Canadian system is that we're colleagues, we're not competitors. So I'm visiting friends and colleagues, and that's the way I see it from both sides. We try to establish a printed electronic network, and we'll try it again. And you will see some work that will inspire us from the PhD of Derek Shipper, for instance. And Mr. Carty, I've known him on many duties, different duties over his career. So it's really a pleasure to be here and to see your new building. So the last time I came, you were in I think the chemistry building or in the nearby, but it's a very, yeah, probably. It's very impressive. I would try to give an overview of what we're doing. I would try to be understandable. I would try to show the feel for the graduate students also. So the specialists perhaps won't learn that much today, but I hope that the general audience coming from the graduate studies will catch some words and where the field is going. And the field is about what we call plastic electronics. It's also called organic electronics, printable electronics. It's all the same in my point of view. We have a nice campus. You have a nice campus. We have a nice campus, I think. So that's the old district in Quebec here. And this is a picture taken about 20 years ago. And so the overall campus is here. That's what we call the main campus. And we have a medical school about 5 minutes from there. And this is a picture taken last year, I guess, this is an official picture from the university. And you will notice that the big change is really about sports. So we're very proud of our football club. They have been very successful, and they have their new stadium, and it's very, very popular. Chemistry, photonics is very important also, and chemistry is here. And I would like to discuss and present to you today our work on the so-called conjugated polymers. And Yuning is an expert also, and I'm sure you have already heard about these new kind of polymers. I call it the third generation of polymers, having the commodity polymers as the first generation, the engineering polymers as the second generation, and this is the third generation. And the key features here is the fact that they exhibit very nice electrical properties. You can move the electrical properties from semiconductor up to the conducting level. They are nice chromophores. They strongly absorb light in the visible, UV, even in the near-infrared range. And since we're dealing with high molecular weight materials, we have a quite good stability for organic-based materials, carbon-based materials, let's say. We have the mechanical properties of the traditional polymers, so you can make inks, you can, they are flexible, lightweight. You can make different objects from the liquid state or from the glassy state, so it's quite easy to manipulate compared to inorganic-based materials. I must say that if you're just looking for application in the electric field, they are not the best candidates. They are not the best materials available. If you're just looking for optical properties for a new dye, let's say, they are not the best chromophore. They are not so stable. If you're looking for just mechanical properties for polymeric materials, they are not the best materials. But what is really unique with this kind of materials is the combination of all those properties within one single material. So what is unique is the combination of good electrical properties, good optical properties, and good mechanical properties, and easy processing. And combination will make unique kind of application, let's say, which is impossible with other types of materials. So you probably have already seen more or less the same image somewhere. So it's possible to make OLEDs, and he has this, for instance, here is one of the world experts in the field with others. So it's possible to make OLEDs. OLEDs are already on the market. It's based on small organic molecules. With polymers, it's much more difficult, let's say, so it's not still on the market. It's possible to make the electrodes made from polymeric materials, and the semiconducting emitting materials are based on organic or polymeric materials. Union is working on field effect transistors. It could be flexible, printed. And today I will spend a lot of time, or some time, let's say, on flexible solar cells, plastic solar cells. And the dream is to decrease the price of solar energy. So everybody is I would say it's favorable. If you ask the population, are you against or pro for solar energy, most people will agree that it's a good idea and it's renewable and quite green source of energy. The problem, if we ask you to pay 10 times more your electricity, probably we say, it's a good idea, but it's not so good. So the problem with solar energy is really the price. And one possibility is to make printed solar cells. And we try with Ian Hill at Dalhousie to establish a center of excellence. We will get the answer quite soon. And with Ted Sargent also from Toronto, we entitled the project the 10-10-10 Challenge. And the 10-10-10 Challenge means 10 years of lifetime. So stability is really an issue with organic-based materials. 10% efficiency, knowing that we receive freely everywhere in average 1,000 watts per square meter. So it's available worldwide, it's free. What is expensive is to take the energy from the sun and make electricity. So the source of energy is free, transformation is expensive. So we're looking for a 10% efficiency means 100 watts per square meter. And the last 10 is 10 cents per kilowatt. The worst place on earth to compete with solar energy is probably the province of Quebec, where we still pay about 5-6 cents per kilowatt from so-called renewable energy, but 10 cents could be competitive on many markets. In Japan, for sure, it's about 20-25 cents now. So the 10-10-10 challenge could be a good point to establish a new market for solar energy and printable electronics. So how it works? Of course, if you're dealing with solar cells, you need one electrode which is transparent, or at least semi-transparent. Most of the time it's based on ITO. It could be carbon nanotube or nanowires of silver. There are new potentials there. But most of the time it's ITO on glass, which is quite cheap. And ITO on plastic, if you want it flexible, it's much more expensive. It's a totally different technique. And you need a counter electrode, could be a printed aluminum, printed silver. And the key point, the key component here is what we call the bulk heterojunction developed by Alan Heger, where you mix a P-type semiconductor and N-type semiconductor. And for some reasons, not that well known, the best N-type semiconductor up to now for solar cell application is a fullerene derivative. It's called the C60 PCBM or C71 PCBM. So this is our N-type semiconductor. And one typical polymer in the field is the regio-regular poly-3-axial thiophene P3HT. It's commercially available now. And if you mix them, they are immiscible. They will make nanocomposites, let's say immiscible nanocomposites. And we want the size domain about 10 to 20 nanometers. Because I will show you later why it's so important, but the mobility is not that high in those compounds, and I will show you in a few minutes why it's so important to have these size domains about 10 to 20 nanometers. And also you need a percolated pathways for both components. If you create here at the interface an electron-hole pair, and then you make electron transfer, those charge carriers have to travel and reach their respective electrodes. And so we need a percolation pathway to get photocurrent. So how it works, imagine this is your BHD blend here. This is the polymer here, which is a donor, a P-type semiconductor. This is the fullerene derivative. This is an N-type semiconductor. And this is supposed to be a photon. And then you have absorption, you have promotion of the electron here in the what we call the LUMO band. The solid-state physicists will call it the conducting band. And so if there is nothing else, you will get fluorescence here. So this electron will just moves back here, and you will recover your energy. So you have absorption from the sun, and then excitation here. But if within the lifetime of this exciton, it can travel to at the interface here, you will get what we call a photo-induced electron transfer. It has to, and that has to occur within the lifetime of the exciton, and it gives you, considering the mobility here, it gives you this size of 10 to 20 nanometers, okay? So if within that time, in the vicinity of this exciton, you have the LUMO of the acceptor here, you will get this photo-induced electron transfer, and therefore you have a positive charge carrier here on the p-type semiconductor, and an n-type or negative charge carrier here on the fullerenes. You have your percolated pathways, you will get photocurrent. If you want to create energy from sun, it's not only about photocurrent, it's about power. And power is the current times the voltage. And the voltage is somehow, it's not true, especially it's registered, so I don't want to say something which is wrong. So it's somehow related, although directly related, to the energy difference between the LUMO of the acceptor and the HOMO of the donor here. So you will get the photocurrent, which is related to the absorption of light coming from the sun, and the photovoltage will be driven by the electronic levels of your p-type and n-type semiconductors. So this is the source of energy coming from sun on Earth, and that, if you integrate everything, you will get roughly 1,000 watts per square meter. If you make semiconductors with a too large band gap, with absorption in the UV blue region, let's say, you will get poor absorption and a low photocurrent. You may say, as a chemist or whatever material scientist, okay, I will make a black compound, I will absorb all wavelengths, and I will maximize the photocurrent. That could be an answer. However, you will get a low photovoltage. You cannot gain on both ways. And so, as it often happens in material science, a compromise is the best answer. And the best answer to design new semiconductors in this field, based on organic materials, is to target semiconductors between 1.2, let's say, up to 1.9 electron volts. It fits perfectly with the visible range. So all materials we develop in our lab are color intense, have beautiful colors, and that could be also an advantage in some cases. So if you want to design a new material for solar cell application based on organic materials, you have to design a material with a band gap between 1.2 to 1.9 eV. You have to take into account something else, is the fact that you want your semiconductor to be air stable, and you don't want them to be oxidized in presence of oxygen in air. You want them air stable, processable in air, and air stable for a long period of time. And so you have to keep your HOMO level below minus 5.2 electron volts. And if you agree that the band gap has to be between 1.2, 1.3 EV up to 1.9, it gives you a LUMO level about minus 3.7 down to minus 4. Considering that PCBM has a LUMO level at minus 4.3 here, so that's the so-called ID polymer you have to design to fit with fullerenes and to maximize the photocurrent and the photovoltage in your resulting solar cell. Physicists from Konarka at that time made theoretical calculation, and I don't want to go in the details here. This is the fill factor. Let's say the efficiency of the overall solar cells somehow. But the point here is very important, is that mobility in those glassy, not so crystalline material is about 10 minus 3. With amorphous silicon, it's about 1. Crystalline silicon is about 100, 1000. Here it's about 10 minus 3, 10 minus 2. When we get 1, we're very, very lucky. Fullerene is about 10 minus 3. So the limitation here is really the mobility of the charge carriers. And considering those limitations, you may expect, in the best case scenario, an efficiency of about 10 to 11% for what we call a monolayer. It's not a monolayer thick, but one single layer, let's say. So 10, 11% means 100 watts per square meter in average with solar cell. And there is a market, and it will fit with our 10-10-10 challenge. So 10% efficiency is feasible. 10 years lifetime, I will discuss later, and 10 cents is still also a challenge. If you make a two-layer system where you have one system absorbing one part of the solar emission and another one absorbing the rest, let's say in the near infrared, and you make it in series, you will add the photovoltaic, and you may expect efficiency up to 14 to 15%. And Yuning left, but I told him that with Alan Heger, we got the right combination, and we expect to publish soon an efficiency about 14-15% when you match everything with the right combination of polymer. I would say it's feasible. If you read carefully the literature, there are some companies involved in this business, and the best people probably up to now is Iliatech in Germany, led by Carl Leo. They reported certified values of 12% from a tandem, small molecules prepared by evaporation. So it's not a printed solar cell. It's not a roll-to-roll printer. It's evaporated. So it's still quite, I would say, expensive to prepare. Konarka, before they bankrupt 2 years ago, roughly, reported 9%. I'm recorded, I will make jokes anyway. I worked closely with 2 companies in the last 5 years, and both bankrupt. So I'm looking for a third partner now. I'm probably not responsible for anything in this business. UCLA Yang Solarma reported 10.4 tandem solar cells. Polyera in Chicago, Northwestern, Tobin Marks and Facchetti reported 9.2. We're not sure they are talking about polymers, oligomers. We don't know the recipe. Mitsubishi on porphyrins, they told me, it's public, reported 10, 11. They even talk about up to 12%. It's based on small molecules made from evaporation. So we don't know that much. If you want to make academic research and scientific papers in the field, I think you have to rely on what is published, and it's not exhaustive and it's biased, but these are among the best polymers reported in the field. I will discuss how we designed this polymer based on Carbazole here. It's called PCD-TBT. I will briefly discuss this polymer developed at Chicago. It's called PB7. And I will discuss our recent work on this, what we call the TPD comonomer here. And there are other examples of nice polymer. Now, really, we have a lot of polymers reported in the literature with data, with efficiency around 8-9%. Every week, you have 8-9% roughly. And everybody's looking for the 10%. So we'll see. How we started, and it's really, I want to tell you that story because it gives you a way how we think, how we make research, and how we design new materials. You don't sit and scratch your head and design new materials. So it goes from experience, literature, mistakes in most cases, you will see. So it started with a graduate student. He's now Professor Jean-François Morin. He wanted to make an original contribution to the field. And he came to me, he said, I would like to work on polycarbosols in the 2000 roughly. And if you want to make it conjugated, you have to link the carbazole units at the 2,7 positions. If you start with carbazole itself, if you start with carbazole and you want to activate the 2,7 position to make polymerization reaction, it's almost impossible. Because the most reactive position are at the 3-6 position in the para position of the nitro or nitrogen atom here. So I told him it's a good idea, but it's not possible. Nobody have done that. It's a dream, but we don't know how to make it. In principle, it's a perfect polymer because this unit is fully aromatic, so it gives you more stability compared to fluorines, for instance. Carbazole is known to be a good whole transporting unit. There is a commercial product, it's called PVK, polyvinyl carbazole, for photocopiers developed by Xerox. It's well known. So Carbazole is a good choice for developing whole transporting unit. And the fact you have the nitrogen here, you can put side chain. You need those side chain to make those polymers soluble or processable. So all electrical, optical properties comes from what we call the backbone or the main chain. And the processing is the fact that we put in fatty side chain that make them soluble and dispersible. Okay? So you need both. And what we like with this approach, it's called alternating copolymer. If you copolymerize Carbazole, which is an electron-rich unit, with an electron-poor unit, you can get different band gap, and that will reduce the band gap also. So quickly, in the alternating copolymer, the HOMO level is more or less driven by the HOMO level of the electron-rich unit, and the LUMO level of the resulting polymer here is driven or pinned by the LUMO level of the electron-poor unit, and therefore you can tune the band gap and reduce the band gap, and that's very important. So he started with this Carbazole here, and the key point, I removed this slide, but the key point, you don't start from Carbazole, you start from a biphenyl unit and you make a ring closure. And therefore you get access to the Carbazole unit. And with this boronic ester derivatives here and with any dibromo aromatic groups, you can make different copolymers and fine-tune the band gap and optimize the optical properties and the electronic properties. So that's an example. The Carbazole monomer is transparent. If you make the homopolymer, the band gap is around 3 electron volts. So it's not useful for solar cell application. If you copolymerize Carbazole with different electron-poor unit, you can tune the band gap from 1.1 up to 3 eV. So you can make the material you want or the color you want with the band gap you want. It's quite easy. One single student can make all those polymers within few months, let's say. And so we made different copolymers, and from the optical properties and from the electronic properties, we were, and using this plot here from Schaber, we were anticipating, I would say, the potential of a given polymer for solar cell application when blended with PCBM, assuming that the morphology is optimum. So if everything is perfect, you may expect something about 10% here with this polymer here, and about 7% with this polymer here. And clearly, if you put a pyridine core here, you should get better efficiencies compared to what I call the benzene ring here, or benzene-like ring comonomers. And you won't be surprised, those polymers work quite well, and it was a disaster with those ones. And clearly it's because for some reason, we have some acidic compounds in the device, and the pyridine were protonated. So the fact we have a pyridine units became protonated with P.PSS, for instance, and that killed the device. So we got quite nice result with this one. And with Konarka and Harry Eager at that time, we were the first to publish an efficiency above 6%. So for some reason, everybody was blocked at 5% with P3HT. It was the first example of a polymer designed for solar cell application that could give an efficiency of 6%. At that time, that was the world record. It survived 6 weeks probably, and someone got much better results. But it shows that it's possible to design, to make what I call a rational design of polymer for solar cell application. And by improving the quality of the device and with YETAO at IMS, it's possible to get up to 7.5 with this polymer, and Halloniger recently reported an efficiency close to 8% with the same polymer. It's clearly in the design of the device that you have this kind of improvement because the electronic properties are fixed, the molecular weight is fixed, everything is fixed. Something where we're happy about is the fact that up to now it's the most stable polymer in the solar cell device. You may expect a lifetime up to 7 years with this PCD-TBD because the HOMO level is quite low, it's quite air stable, and it's fully aromatic. The Carbazole is fully aromatic, so it's more stable. And so we're looking for the 10-10-10 challenge, so we have about 7% efficiency and a 7 years lifetime and probably 70 cents per kilowatt. So we reach at least the 7-7 challenge with this polymer. It's a quite robust polymer. It's commercially available, and it's studied worldwide as a benchmark polymer if you want to calibrate, let's say, your equipment, or if you want to make comparison with new polymers. It's a good polymer. Anyway, Yang and Lupin Yu at Chicago reported in 2009 also this very nice polymer, and now it's possible to get up to 9.5% with this so-called PB7 polymer. And we look at it and we said, okay, that's very good, but it's not perfect. And the fact it's not perfect because this unit, even for an organic chemist, it's quite complicated to make. It's not so easy, and we're certainly not dealing with low-cost material. This unit is not so complicated, but this comonomer is not. So we decided to go to this kind of structure here, where you keep this, what we call the BDT comonomer, and we made this new symmetric and low-cost comonomer to check or compare what we can get with this polymer. So we made, in few steps, this comonomer here, and the BDT here. To make a high molecular weight polymer, you have to rely on the so-called steady coupling. So you need thin derivatives to make high molecular weight materials. It's not perfect, but we were able to get this polymer. And with Yetao at IMS and RC, we were able to reach up to 7% with this polymer. And Beaujuge, McGehee, and Frechet at KAUST. If you really want a strong competitor in the field, KAUST is a good place. King Abdullah University State and Technology. They reported that if you slightly change the side chain here, you can get up to 8.5. So it's good news, bad news. The bad news is the fact that you have to make different side chain that will change the morphology, not the optical properties. The side chain won't alter, won't modify the electronic band gap, the optical properties. It will just change the solubility, the processability, and also the final morphology when you blend it with fluorines. And it's hard to predict. So you try, you make, you see, and you do your best. So instead of, look, C8, ethyl-hexyl side chain, ethyl-hexyl side chain, C7, 8.5. Impossible to predict. So it's about 8.5 with this polymer. It's quite air stable, not so complicated. It's good also for thin film transistors, so the mobility is about 0.1 here, but it's quite air stable. And if you change the side chain and the morphology, orientation, crystallinity, and so on, you can get up to 1 in terms of mobility, which is quite good. It's comparable to amorphous silicon, for instance. So even Yuning would be pleased with this kind of polymer. So Waterloo is coming. My students are curious. You know, with time we said, okay, I'm a polymer chemist. I'm reading macromolecules. I'm reading this kind of journals, and that's it. But the graduate student, they read everything. But we were pleased the fact that they publish in chemistry materials. So you can publish in JACS, but chemistry materials, you will catch our attention. And that's the PhD work of Direct with the late Kate Fanyu. And they show that it's possible to make reaction with CH bonds. And for us, I didn't know, I was not aware, it was impossible. Based on palladium, I mean, the catalyst is not so fancy. It's not so complicated. So they made aromatic compounds here. The yield is 87. And it's exactly a conjugated oligomers here. I must say that for polymer chemists, this yield is not high enough. If you want to get high molecular weight materials, you need a yield of, if you take the Carruthers equation, you need a yield of 98, 99% to reach a degree of polymerization of at least 50. If you have a polymer background or polymer chemistry background, you need a yield of 98, 99% to use a reaction to make a high molecular weight materials. There is another point. They also observed that the mono substitution occurred. And for us, it's a disaster because if you have a defect, if the selectivity is not perfect, all those defects, side reaction, will be included in your polymer. You cannot remove impurities. You cannot crystallize a polymer and remove the impurities. So the polymer will bring all defects, all side chain, all side reaction, and all problem. So the selectivity and the yield to make high molecular weight polymers is very high. So I'm saying that the standards for polymer chemists are much higher than for the organic chemists. So that's the message. Another work at the same time from Ozawa in Kyoto showed that it's possible to make this very important polymer, P3HT, from a direct correlation polymerization. The head-to-tail coupling is 98%. So it's a well-defined polymer from this direct correlation. So you have the coupling between the bromo here on the CH bond here. So my student came to me and we said, TPD is the perfect monomer for us because you just have two CH bonds exactly where you want. And there is no other CH bond here. And if you take a bithiophenene and you make the dibromothiophenene instead of the stenolated bithiophenene, so this is the typical reaction to make this polymer for thin film transistors, let's say. And that's the reaction my student proposed to me 2-3 years ago. And I didn't believe it. I said it won't work. It will never work. Come back when it works. See you in 1 year. Not only it works, but we got higher molecular weight. So instead of 10 number average molecular weight, we got 55. And we think that these CH bonds here are not reacting because they are somehow sterically hindered by the side chain here. And we check by NMR. We compare the steady coupled or steady polymerized polymer and the polymer obtained by direct heterorelation. It's comparable. You just see some little peaks here which are related to the what we call the N groups. If you have a low molecular weight materials, the N groups become more important and you see those extra peaks in your NMR. So it's a well-defined alternating copolymer. It made a good splash in the field because it simplifies completely the chemistry. And that's how we made transfer this message. It was published in Angeventi, so they're looking for TOC which are spherical. So we tried with ice hockey, we made it. So we used curling. So instead of the steady coupling, you get, in some cases, higher molecular weight. It's certainly eco-friendly. You get rid of any thin derivatives. You reduce the number of steps. Clearly, you reduce the cost of your materials for comparable applications. So it's very, very important in the field. The first time I gave that talk, I said it's a gift given by the organic chemists to the people involved in polymer electronics. Frankly, it will really change the way we're making polymers. I discussed with big companies, if your materials, as good it could be, involve a steady coupling, they cannot make large-scale production. It's forbidden, at least in Europe and North America. Okay? Steady coupling is not allowed for large-scale production. So we made series. We like TPD because, I repeat, there is no problem of selectivity. You just have two CH bonds. So we made different polymers, and we checked by NMR. So well-defined, no defects, alternating, well done, molecular weight about 50,000, which is good in this business. And we sent it to Alan Heger, the first polymer prepared by direct correlation for solar cell application. We got 6%. But it was in 2012, so in 2009, Alan was happy with 6%, but in 2012, he called me and he said, Mario, perhaps you're very happy with your synthesis, but your materials are good, but they are not great. So I'm looking for great materials. So we're still working for great materials. So, but at least it showed that it's possible to get well-defined, efficient, quite efficient materials in this business. We also try with, it's called iso-indigo comonomer, and we got good molecular weight and something comparable that you would get from Suzuki coupling, for instance. Problems. So that was a nightmare for us. If you want to co-polymerize fluorines and bithiophenes, and bithiophenes is a very important unit in the field, you get insoluble materials. And the reason why is because there are some traces of what we call branching. So the selectivity is not perfect, and branching will cause cross-linking, and cross-linked materials are not soluble anymore. Okay? So a little branching will become cross-linking, and processing will disappear. So to show his point, Cambara said, okay, if I block what we call the beta position with methyl groups, so you just have two remaining CH bonds here, and you get soluble, processable, with a number average molecular weight of about 30,000 of useless material. And why? Because the fact you put methyl group here will make a twisting of the backbone. It's not coplanar anymore, and you lose all electrical and optical properties that you were looking for. So it showed a point that selectivity of the coupling is important and could be a limitation, but it didn't bring any new polymers useful in the field. It was a very, very bad news for us, but we were not so surprised by those results. And another way to see it is the fact that if you make P2HT from steel coupling, let's say, the beta position are not reactive for steel coupling, because coupling will just occur where you have a bromo group and a tin group. But for direct correlation, the number of alpha proton will decrease as a function of the molecular weight, and the probability of branching will increase with the molecular weight, because the number of beta protons here will increase compared to the N groups. So it's not surprising that when you increase the molecular weight, the selectivity will decrease, and you will get cross-linking, branching and cross-linking. So we have students, and you know, if you tell a student it won't work, there is a wall, and you will hit the wall. Whatever you do, it's the best motivation. So I have a student, he said, okay, perhaps he's right, but I will just repeat the experiment, just in case. And he showed that at the beginning, the molecular weight is low, but it is soluble. It goes up to, let's say, 10. It decreases, and then you get just insoluble material, so cross-linked materials. Let's say it's cross-linked. But at the beginning, it's soluble. I would say it agrees with this idea here that cross-linking will occur as a function of time. So what he's done, he chose a solvent where the system is less reactive, so we slow down the reaction, and we follow the kinetics. And that's really the typical step growth polymerization mechanism, where you have an increase of the molecular weight as a function of time. So if you follow it carefully, you can go up to 26 number average molecular weight. If you wait too long, you get fully insoluble materials. Is it related to the fact that it is cross-linked, or the molecular weight is too high and processability is decreased? We don't really know. But it's possible, if you stop the reaction here, to get soluble, processable, and useful material. I said, yeah, perhaps you have been lucky. Try another set of monomers. Oh yeah, we followed also the UV visible. So look, at the beginning, low molecular weight as a function of time. And finally, in red, you have the typical Suzuki polymerized materials and comparable UV visible absorption spectrum from this direct correlation. So you try with Carbazole bithiophenol, same thing. Step growth polymerization. If you proceed for a too long period of time, it becomes insoluble, totally insoluble. But you can keep here with a yield of 85, 90%, a molecular weight around 55. He followed, so that's the typical Suzuki coupling. And if you follow it as a function of time, you get comparable UV visible absorption. So you have to have a time control of the polymerization to achieve well-defined processable polymer. NMR is I would say the right tool to compare. So this is the NMR spectrum obtained from the Suzuki coupled polyfluorine, and what you get from direct heterorelation polymerization, comparable, totally comparable. The same for the Carbosol here, you get more or less the same material. So it's possible to get comparable materials with direct correlation or Suzuki coupling. We started with Carbazole, and it's called DPP, diphenyl pyrrolodione something. A very important polymer. A lot of CH bonds. Sorry. Once again, if you compare with Suzuki, if you control the time of polymerization, you get different molecular weight and comparable NMR. So it's fully soluble, processable, comparable data. We send those materials to Union Lee here. It got even better better hole mobility with those materials prepared by direct correlation. This important PCD TBD polymer prepared by Saint-Jean Photochimie, for instance. Usually we use the Suzuki coupling. Now we use this dibromo Carbazole, this unit with a lot of CH bonds. If you're very careful, it's quite selective. Those protons here will react first, and you get comparable NMR spectra and comparable UV visible absorption, comparable hole mobility, and we will see soon if we get comparable solar cells from those materials. But clearly we will decrease the cost of fabrication of those polymers. We decided to make this polymer developed by Xerox. It's called PQT12 if you are in the field. And we've done that in this way. It works quite well. However, it doesn't work in this way. And I'm talking to the chemists here. So in principle, if you polymerize this or that, you will get the same copolymer. However, we think that if you put a bromo group here, this is an electron withdrawing moiety, it will activate or make this CH bond more acidic. If you put the bromo group here, but you block this beta position with an alkyl side chain, selectivity is good here, selectivity is good here, and you make the coupling in the right position. If you do the opposite here, you have some, we think, some cross-linking here. So that's still a limitation. We're not sure. Perhaps it's a problem of selectivity and finding the right ligands and the right catalysts, but it's a limitation. With Yuning, look, we got similar results here. If you polymerize this with that, you get the polymer P1. If you polymerize this with that, in principle, you get the same polymer. However, if you polymerize with the bromo and the methyl group here on the CH bond here, you get the mobility up to 1 and a number average of 45. If you polymerize this unit with the bromo and non-protected group here on the methyl group here and CH, you get a mobility of 0.2 and a number average of 15. So it's not exactly the same polymer depending how you choose your monomers. Okay, so you have to be careful. It's not the same UV vis absorption spectrum. So it's not exactly the same polymer. So that has been done with Yuning, showing that it's possible to reach mobility up to 1 from polymers prepared from direct heterorelation polymerization. So yeah, it's good. in conclusion, these are our general conditions to slow down and have a better control of the polymerization reaction. It's not the best condition to make a quick reaction for small molecules. It's really typical for conjugated polymers. So we need a palladium source. Palladium acetate is good. This is a ligand developed by Ozawa. We like it. We need pivulic acid developed by Fanyu. Cesium carbonate, 3 equivalent. We prefer toluene and THF. Boline THF is good. You can polymerize any aryl, we think. You can polymerize any aryl bromo group with on any CH bound on the thiophene unit. So bromo, aryl bromo, fluorine bromo, benzene bromo, carbazole bromo, what you want on a thiophene unit, protected or not protected. If you're careful, you will get the well-defined copolymers. That's what we believe. So it will replace Suzuki coupling for most cases and Stili coupling in some cases here. Limitation here. If you have the bromo on the thiophene unit which is not protected, there are some problems of selectivity. So this is still a limitation and this is still a subject of study. So I think it's good news for the field because, I repeat, it will simplify the synthesis, lower the cost. We want to make microelectronics. So even ppm of tin or ppm of boron derivatives will decrease I would say, the overall properties of the materials. In microelectronics, it works with silicon because it's 99.999% pure. With this kind of material, it's full of side products and remaining catalysts. So if we can get rid of any tin or even boron compounds, it will certainly, I would say, increase the lifetime, the stability, and perhaps the properties. So with Lauren Mercier, who studied here, so Waterloo also is involved in this. I think she did BSc here? Yeah. And learn about chemistry with Eric, I remember. So these are the tools that we have in polymer chemistry to make these materials for plastic electronics. It's based on Stili. I don't like Stili, so it's like a hammer for us. I don't remember why we put a soft for a coupling reaction. Probably it's not the best picture here, but Suzuki is quite good. And we hope with fine-tuning and some optimization that this direct correlation polymerization could become a new tool. I will tell you, all companies now in the field, BASF, Merck, all of them, they are working with this direct correlation polymerization, looking if they can make comparable materials to the traditional approach. So Waterloo was involved a lot with Yuning, Derek, and Eric. Support is important, but above everything, it's really the support from the students. So it's a picture taken not this summer, but 1 year ago. And with this, I will stop here and thank you for your attention.
Thanks very much,
Thank you.
Mario. Are there any questions? Derek?
I'm wondering where you see the cross-linking later on in the reaction, and you're proposing that it's just a simple function of the length of the polymer chain. Could it also have anything to do with catalyst stability?
Maybe.
Perhaps, I don't know if you've done any catalyst stability studies. Maybe the catalyst is degrading into something else that is now active for functionalizing the C3 position as opposed to C2?
Okay, I will have to repeat the question they told me. So is the problem observed of cross-linking observed as a function of time related to the stability of the catalyst? I'm curious to know how the catalyst will induce a cross-linking of the materials. It will stop the reaction, but it will induce the cross-linking of the material?
Well, just if you get degradation of the catalyst into something else,
maybe.
like maybe palladium black or palladium nanoparticles is somehow an active catalyst for the C3 position.
Maybe. Now what we think, and perhaps you can answer, that's more a question I'm asking you. My student would say that this bond is so reactive if he doesn't see something to react with, he will make a debromination reaction. So they believe that this CBr bond, especially when the H is surrounded by something which is crowded, wants to react and makes a debromination reaction. And so it's not the stability of the catalyst, it's the stability of the bromo-thiophene unit. The bromo-thiophene unit is not so stable. The bromo-aryl groups are quite stable. They will survive for many months, even in air. But the bromo-thiophenes are not so stable, and now we're not sure. So I gave you the first explanation that you will find in the literature. I'm not sure it's the right one. Okay, so I just reported what is. If you read it, they will say that branching will increase as a function of the molecular weight, and it could be that reason. It could be the stability of the catalyst, making side reaction and cross-linking. It could be also the stability of the bromo. And when it becomes insoluble, for the soluble material, when it becomes insoluble, we think it's related to the fact that we reach a too high molecular weight. If you perform Yamamoto coupling, have you ever done that with nickel? It's so fast, so reactive that you think cross-linked materials, but it's insoluble because it precipitates and the molecular weight is that high that it's not processable after all. So you have to stop the reaction to keep it in the moderate molecular weight. So in the lab, I have different students with different opinions. Stability of catalyst, maybe. Stability of the monomer, and a too high molecular weight. We don't think it's related to cross-link. But we have still a paper in debate because it's hard to characterize a non-soluble polymer. So to show what is the reason of insolubility, NMR is useless. It's very hard. And you won't see little defects from infrared, for instance. So it's open. So most people have made similar observations. So the data I reported could be reproduced by many people in the field and have been observed by many people. The explanation is still open, in my point of view.
Any other questions? One general question about the technology. So I assume that the benefit of using organic solar cells versus inorganic solar cells is in the cost.
Yeah.
And you can cover a greater area for lower cost.
The advantage of solar cells, organic solar cells, in average, is the cost, lightweight, flexibility. So if you want to travel with a solar cell, it has to be lightweight. So if you talk with the U.S. Army, they don't care about cost, weight, and stability. Efficiency also. So it depends. So lightweight, flexible, you can put solars. If you talk with the architects, something I didn't put here, if you want to make semi-transparent windows made of solar cell, it's more or less, it's difficult, let's say, not impossible. It's difficult with silicon material. I know it's possible because some people here are doing that. But it's quite easy with organic material. You make a thin film, you change the thickness, and you can get the color you want, okay? So semi-transparent could be an option. Lightweight sometimes. It depends where you want to put it. Flexibility, the color. If you talk with the Army, they would say that I need a color. They wanted us to make a textile, a solar cell within the textile for camouflage. So you needed green, brown, gray. The first material we've done for them was indigo. And then we moved to pink. And we almost lost the contract. But it's a question of time. Sometimes it's hard to predict the color of the final product. But remember, we got pink, very efficient pink. And for camouflage, they really didn't like it. A quick story. I worked on biosensor many years ago, and we were very pleased by the color change. But the first microbiologist I met is still colorblind. So he was not impressed at all. And he looked at the UV spectra to be convinced that it works. So it depends. So lightweight, could be cost. If you talk with Hydro-Quebec, it's cost. And they don't care if you need 10 meters or 20 meters, we have a lot of space, they don't care. It's the cost. If we have, we discussed this during the lunch, if you want to make a solar cell for your phone, and you open it, and it could be indoor also. It's quite efficient even indoor. So you can recharge your batteries. So the lifetime of a phone, a smartphone, is 1.5 years. So if you have a lifetime of 2 or 3 years for your solar cell, it's enough. Roof for the cars, for instance, could be made from solar cells, and you can put your iPhone on this. So different market, different qualities. Overall cost will always come back.
May I ask you, for your solar cell work, have you ever tried with the molybdenum oxide before? Because people are
Yep.
recently using.
Yeah, okay, you know the field. So if I've used different electrodes and substrate, like molybdenum oxide, yeah. Yeah, we've made what we call inverted solar cells with sol gel processing. So with Hydro-Québec, for instance, they want all processing made from sol gel or ink, Dr. Blade. They don't want to evaporate anything. So no vacuum, no low reduced pressure. So it's somehow specialized what you ask for, but so we now use what we call inverted solar cell, which are much more stable. There is no, I would say, reactive electrodes, and it's quite useful. ITO, in my point of view, ITO is still a problem. ITO on plastic is very expensive. So with Hydro-Québec, for instance, they decided that they don't need the flexibility, so it will be on glass. So all processing has to be done on glass, ITO on glass, and so on.
The reason I asked you the question is because for your 10-10-10 challenge.
For my 10-10-10 challenge, yeah.
Yeah, whatever.
Yeah.
You have made a series of polymers with expecting that you can reach 10% with your final one, but the results, what you said, what is very tragic. And you have little bit mentioned that may be because of PSS.
Yeah.
So if you want to expect that to be 10%, maybe you can think about
Get rid of PSS.
Put the molecule
You're right.
aside, so probably
It's beyond the scope of this talk, but be sure we and the community is working on this. Get rid of ITO for cost, get rid of PDOT because of the acidity of PDOT, okay? That studied worldwide. If you want to have a good review and a good knowledge of the field, Frank Krebs in Denmark is really the leader of the engineering of solar cells. He's the only one among the few in the world taking care of the processing, large-scale production, module. You can have 10% on a 4 millimeter square electrode, but if you want to make large panel, you need connection, you need a lot of things. So Frank Krebs in Denmark is really the leader in this terms of engineering. Really, in our case, we're limited to the material production and design. Yep.
Any other questions? Jean-Jean?
Yeah. So the polymer is conjugated polymer. It's usually very rigid.
Yeah.
So, but you make this polymer soluble, processable. Have you paid any attention to the viscosity and the rheological property of your polymer, or in the literature there is some discussion of this?
Yeah.
Compared with coil polymer.
Okay, the question was about processability, viscosity, and printing, and the printing.
Rheological profile difference with the polystyrene, for example.
Huh?
Coil polymer. So any difference, or they are very similar?
If they are similar to polystyrene?
Yeah, something.
Not at all.
Not at
Because polystyrene is a quite flexible materials, and just when we make GPC measurements, we compare to polystyrene, but it means nothing because really the molecular weight that we are reporting are compared, but it's not an absolute measurement. So if you talk with processing, of course you need the right viscosity and the good molecular weight to get the good mechanical properties. I must tell you that most people, they make a new polymers, they're looking for an efficiency on a very tiny unit, and then if it's stable enough and blah, 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 we will take care of this. It's very important. If you talk with European companies, all polymers I've shown today are soluble in chlorinated solvents. And processing are done in chloroform, dichlorobenzene, and this kind of materials. If you talk with European companies, it has to be soluble in xylenes. And even toluene is a toxic solvent for them. Okay? So you have to redesign the materials, the side chain, the viscosity, morphology. You cannot predict what you get from chloroform to xylenes, or even chloroform to dichlorobenzene. So it's very time consuming, very, very frustrating. Very. Because overall, the morphology will drive the efficiency.
Yeah, so, yeah, okay. So all the time season you're talking a lot about the world record, how good, but we don't know too much about why this, why.
The why, okay. The why is related to morphology. I will be frank with you. We don't know. So we observe, we can explain, but we cannot predict. And till we cannot predict anything, it's just trial and errors in my point. So after all, you can say, oh yeah, of course, I now understand why it didn't work. If it was so obvious, tell me before. I mean, and we won't make it. So with Michel Côté at the University of Montreal, he's able from DFT calculation to predict the band gap and the electronic levels. And so now we use those in the gas phase, okay? And also how to say, if it's planar, non-planar, twisted, and so on. Nobody, to my knowledge, can predict the solubility, processability, and the morphology. Even for a simple device like thin film transistor developed by Yuning, it will give you completely different mobility if you have an edge-on orientation or a face-on orientation. Okay, for the charge transport, it will be completely different. I think it's hard to predict. There are some observations, but there is no trick that if I put those side chains, it will be face-on or edge-on. So it takes time.
So I think small, so I'm not sure whether I'm right or wrong, because I'm not looking at this area. The small molecule is better than polymer. Is it because the small molecule has a good packing?
Okay. I didn't mention perovskite, which are the very important materials now in the field. Small molecules, people will debate. So the purity is much better. It's much easier to purify small molecules by sublimation, whatever. Okay, so it's highly pure, reproducible. Everything is good. Viscosity is not that obvious. And also, if you make, especially for solar cell application, you make an immiscible blend kinetically, and with time, thermodynamics will win. And perhaps you will get demixing of both components, crystallization of both components, and a failure of the device. So in the field, nobody really investigated the lifetime and stability of small molecules for solar cell. It's quite good for thin film transistor. And just to complete the answer, the German company, Eliatech, it's not bulk heterojunction. They make a two-layer system. So they make a clean, well-defined interface. Okay. So there are, if you invite someone like Guy Bazin at University of California, Santa Barbara, he will say small molecules are the next things. People from England, perovskite, and today I will tell you polymers will be the final answer for sure. We're all biased.
Dr.
Leclerc
has some other appointments before he leaves, so I hope you'll join me in thanking him for an excellent presentation on a challenging problem.
Thank you.